Okay, so starting with homework questions. Do you have a couple homework questions, or you only have lab questions?
I have a question on my process for 14.
Okay, let's go ahead. Let's look at number 3 again real quick because we didn't have the video going for that. Everyone should be able to see this. No one ever uses the chat to ask me questions, but we'll see if that happens today. So let's go ahead. Let's look at number 3 real quick. If somebody can read out number 3.
I got it right here.
Sure.
Okay, so a heat lamp produces 32.8 watts of power at a wavelength of 6.51 micrometers. How many photons are emitted per second? And then they also give us that 1 watt is 1 joule per second.
Oops. Writing things down wrong. 1 watt equals 1 joule. 1 second. Okay. And the question we're asking so when we look at a problem, we want to do this kind of analysis, right? So all I did was I wrote down all of the explicit information that was given to us. I wrote down all of the technical information. I wrote down what the question is actually asking. There's a real tragedy. I saw it in the quiz. I have your first quiz to get back to. We got the second quiz today. People didn't answer the question. There's on problem 2 of the quiz, they just didn't answer the question.
Like they didn't attempt it, or they just didn't.
Their
answer was completely separate from what you'd asked for.
They did like the first part, but not the second part. So like they were like, oh, I know how to do this, and they just did it and moved on without finishing reading the problem. So they didn't. So it's always important to write down like, what is the question actually asking? So we want to get photons per second. Now, the thing that challenges most people for this is the units of watts and how we deal with that. But since we're doing everything in per second, 32.8 watts is just joules per second. And we want it in per second, so I can pretty much just multiply by, I want it all in 1 second right away. And I'm going to get 32.8 joules. So that's a whole lot of joules. And what we have to say is, okay, we're going to get this number of joules from some number of photons. We say, okay, what's the typical energy of a photon? And you already answered, so what's the typical energy of a photon? What's the range? What values do we usually see? Just really big or really small.
That's the one.
I know, it put you right on the spot. So you remember when we were doing calculations yesterday in class?
Yeah, I'm trying.
Do you remember just the exponent? Was the exponent positive or negative? Right, we had like some number times 10 to the...
Positive? No, negative.
Negative.
Okay.
And it was typically on the order of 10 to the minus 19, right?
Oh, yeah. Okay.
So when we look at that, we can already, before we do our calculation, we can say that if a photon, so that's joules per photon. If we look at that, I want to make sure it's on the screen. If we look at that and we say, okay, how many...
Yeah.
So, are we going to need a lot of photons or just a few photons? If we want to get that energy up to 32 joules.
We're going to need a lot.
We're going to need a ton of photons. And now you can see, based on the units here and the units here, all we have to do is divide by the energy per, the photons per unit energy. Or sorry, multiply by the joules per photon, which is multiplying by the photon per unit energy. So what we have to do is we have to figure out what our energy, for this particular case, the photons have a particular energy associated with them, and we have to figure out what that energy is. So how do we convert wavelength to energy?
HC over V.
There we go.
HC over nu.
Lambda.
Or lambda, sorry,
yeah. Yeah. So E equals HC over lambda. We can go ahead and just plug in numbers here. We got 6.626 times 10 to the minus 34. We got 2.998 times 10 to the 8. We've got 6.51 times 10 to the minus 6. Notice I just snuck in the micrometer conversion real
Yes.
quick there. If I wanted to follow all of the units around, this is meters per second, this is meters, this is joules seconds. Seconds cancels out, meters cancels out. This is just going to give us units of joules. Whoa, we're going to get a really low energy if I'm doing math in my head correctly. Because we got minus 34, minus 6. Oh, wait, no, that's not as bad as I thought. Minus 6 inverted would be like times a plus 6. So, calculators. We're expecting something on the order of minus 19, but since this is actually a really low wavelength, we're expecting, sorry, a really high wavelength, we're expecting a lower energy. So we're expecting something that's probably going to be more like minus 20, minus 22-ish.
Yeah, let me do that real quick for you.
I had 3.0514 times 10 to the negative 20. But they can verify that. Make sure I did it right.
Let's see. 6 and 6 cancels out. You got about a 3 left over, I believe it. And you got negative 34, 8 and 6 is 14. Yeah, that's
Yeah.
totally going to be it.
Yeah,
Yeah.
3.051 comes up to the negative 20. Yep.
Great. So now, this isn't the answer. I almost boxed it like it was the answer. This isn't the answer, right? This is just the energy per photon. And technically, every time we've done this calculation where this is energy of a photon, this is joules per photon.
Yeah.
Right? That's the energy of an individual photon. That's the other part that people miss out on. They get this unit of energy, and then they don't know what to do with it. But knowing that this is joules per photon, and this is the joules we want, we just take the joules we want, divided by the joules per photon, we get a number of photons.
Yeah.
So we get the 32.8 joules times photons have 3.05 times 10 to the minus 20.
That's
So,
gonna get us a lot. That's gonna get us
like 10 to the positive 20. Yeah.
21.
Yeah, well, 10 times 10 to the positive 20,
Yes.
10 to
Yes.
the 21. I'm going to put an explicit positive on that just because so much of what we've done is negative exponents. I want you to make sure I didn't forget a negative sign. That's intentionally positive.
I got 1.07.
1.07, so like a huge number of photons, right? Cool.
Nice.
I'm just going to put approximate there. And we can go ahead and put in our photons per second, right? Because we multiplied by 1 second earlier, so this is all per second. That's how we handle it. It's pretty straightforward unit analysis, but there's 2 tricks. Understanding the watts, and then understanding that the energy of the photon is actually joules per photon. And then we also had a question about number 14.
Yes.
Number 14 is the hydrogen atom spectrum.
Yeah.
So we went over this a little bit yesterday. Let's go ahead and look at it now. Your question was mostly procedural.
Yeah, I just want to verify that I did it correctly.
Part A, you okay with part A?
Identify which transitions. Yeah, that's just
Yeah.
looking at the wavelength.
Yeah, so part A, we're using the fact that we did this calculation yesterday in class. We realized that n final equals 1 is going to be all of our ultraviolet. That's going to be wavelengths shorter than 400. N final equals 3 is going to be our infrared. That's going to be all of our wavelengths greater than 700-ish. And then n final equals 2 is going to be anything between the two, the visible spectrum. So we can take the 5 wavelengths that are given and we can identify which part of the spectrum they're in to get their n finals. Part B is where it gets a little bit tricky and we have to be a little bit careful because there's 2 parts going on in part B. First thing we have to watch out for is, well, first off, what equations are we going to use? There's 2 equations that we need to use.
The energy of a photon, so energy equals hc over,
Yeah.
and then the
Rydberg equation.
Rydberg equation.
So I'm going to put this in 3 equations. I put these together in the past. So we've got the energy, the change in the energy of the atom is the Rydberg constant times 1 over n final squared minus 1 over n initial squared. Don't forget your negative sign. The energy of an atom, the change in the energy of an atom is either going to produce or absorb a photon. That photon has to be positive energy, so regardless of the change in the energy of the atom, whether it's a positive or negative change, the photon is going to be positive energy. So I just do absolute value rather than thinking about the process. And then we know that the energy of the photon is hc over lambda. So we can use this to kind of backtrack. Now I do want to mention something else. Whoa, as I throw a pen across the room. We have another Rydberg equation, another Rydberg constant. So in this case, the Rydberg constant is, what is it, 2.18?
2.1, yeah, 2.179, 2.18.
Times 10 to the negative 18?
Negative.
Joules?
Mhm.
Okay. There's another Rydberg equation which says delta E equals negative Rydberg 1 over n 2 squared. Wait, I gotta remember this now.
Yeah, it's like 2, 1, 2.
N1 squared minus 1 over n2 squared. This Rydberg constant, I'm going to call it RH just to give it, so this is the Rydberg constant for a hydrogen atom. It has the value of 1.07 times 10 to the positive 7 inverse meters, if I remember correctly. It should be on your equation sheet.
This one says RH equals 2.18 times 10 to the negative 7, and regular R equals 1.097 times 10 to the 7.
0.97. So for consistency, okay, first off, that looks terrible. For consistency, I'll just call this R.
Okay.
1.097 times 10 to the 10 to the positive 7 inverse meters. So this equation has an extra stipulation on it to make this work. This is only emission. And if I remember correctly, they don't even call it delta E, they just call it hc over lambda.
1 over lambda, but
Oh, 1 over, even great, better. 1 over lambda. This only works for emission, and it only works when N1 is less than N2. This equation, the reason this equation is on there and this equation is important is this is the equation that Rydberg originally wrote down. This is the one where he essentially observed the spectrum that we looked at on Wednesday. And he said, oh, I don't know why this is happening, but I can make measurements of the separation of the lines, and I can make an equation that relates to the separation of the lines. Just pure empirical observation found an equation that worked. They had no idea why there was the 1 over n squared. They had no idea why it was this number or why it was 1 over lambda, but it worked. And so they're like, great, we're going to do that. With this stipulation that n2 has to be a bigger number than n1. That guarantees, wait, or is it n1 greater than n2? I have to think about this now.
no, it's N1, because
Which one's first in the equation?
N1.
N1, N2. Is it negative in that equation?
No.
Nah, that's the thing. Okay. It's not negative in that equation. So the reason that it's not negative and that we have this stipulation is because we know all this criteria and that missing negative sign is all to make it so we're guaranteed to have a wavelength that's positive, right? Because if N1 is always less than N2, this is going to be like 1/4 minus 1/9. 1/4 minus 1/9 is going to be a positive number. So that's all to guarantee that this comes out positive.
Yeah.
Right? So if we're doing emission calculations and we've got things in terms of wavelengths, this equation is nice. It's quick. It's a little bit quicker than doing this two-step process, but it only works in particular cases. This one works every time. So I prefer to just learn one equation rather than like learning an equation that works some of the time and another equation that works for other times. Like I'd rather just learn one. And then not have any weird stipulations about my end finals. End final and initial can be any value, right? It can be for emission or absorption. We just have to remember that the wavelength has to be positive. Now, the reason I bring all of that up is because it becomes tricky when we're looking at the lambda and we want to know, is this energy of the photon, is the atom gaining energy or losing energy, right? Because that actually matters for this, right? So if I calculate my energy of the photon, I plug it in here, then I'm like, oh, but I'm going to take the absolute value. Is my energy of the atom going to be positive or negative when I'm calculating this, right? So for emission, my final value should always be larger than my initial value. I know that this should be a negative energy of the atom. So I know that the atom should be losing energy. So when I do that, I can kind of I can figure out whether the energy, changing the energy of the atom is positive or negative from the photon energy, and the logic of whether it's emission or absorption. If you don't do that step, like so, these problems are for emission, right? Atom losing energy. If you just say the energy of the photon is positive, the energy of the atom is positive, you will mess up your signs, right? Because if this being positive or negative actually changes the calculation. So you have to watch out for that. So when we actually do our calculation here, let's just pick one of the 4 points and try it, or one of the 5 points. Which one do you want to do? A, B, or C, or D?
486.13 nanometers.
486.13 nanometers. We're just going to do C real quick. Our energy of the photon would be 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8 divided by 486.13. I'm going to do another quick trick there, 10 to the minus 9. This is how I do my unit conversions, right? I know I could switch this to be 4.86 times 10 to the negative 7, but I can just plug that into my calculator just as well. And it makes it so I'm not going to mess up. I know nanometers minus 9. That's the way I do my conversion super quick. I like it. If we can calculate this, we've got 3, we've got like 5. I can't do that in my head. If you've got a calculator, help me out. So, 3 times 6.6 divided by 4.86. I can't do that in my head. Can't do that in my head. You can't? Let's see. It's going to be like 21 divided by 5 is going to be like 4. 4.5.
86.
Times 10.
Negative 19.
I should have been able to guess that just because of the wavelength. Almost all of our visible light spectrum is 10 to the minus 19, but I was trying to like do my additions and subtractions. Whoops. 4.86 times 10 to the minus 19 joules. Notice this is the positive energy of the photon, and we have that the absolute value of the energy of the atom is equal to the energy of the photon. And this is where we have to do a little bit of thinking. Should the energy of the atom, we actually want to know whether the change of the energy of the atom is positive or negative. Since this is emission,
Should be negative.
it should be negative. So the change in energy of the atom is going to be negative 4.086 times 10 to the minus 19, which is going to be equal to negative 2.17, I'll just call it 2.18 times 10 to the minus 18 times 1 over, I know the end final because this is visible spectrum. The end final is 2, so that's going to be minus 1/4 minus 1 over, yeah, let's, I'm just going to call it an initial squared. I'm going to go with 5 as the answer. I'm just guessing based on the wavelength, but that's because I'm really familiar with this equation. But let's go ahead and do this. Notice this is set up. We know that an initial needs to be a positive number,
Cause then it wouldn't be a negative.
right? And so we know that this whole subtraction needs to be a positive number, right? Just thinking about it. So you notice that these two negative signs are going to cancel each other out, so this parenthesis is a positive number, which is what we want. So we're going to do 4 divided by 20 is going to be like 2 times 10, no, 20. Wait, no. Why can't I do that in my head? 0.2?
Yeah, I got point.
187.
Yeah.
Let's get the actual number, the 0.187. 1874 is equal to 1/4 minus 1 over n initial squared. So again, notice I can go ahead and replace this 1/4 with just a 0.25. So 0.1874 minus 0.25 will give me a negative number. My negative sign will again cancel out. That'll guarantee my n initial is positive. So what is 1.87 minus 0.25?
Negative 0.626.
I'm going to get rid of the 0.0626 is equal to 1 over n initial squared. Oh, what's 1 over 0.0626? I think I know what it is, but I want to double check.
15.97.
Ooh. Oh, that's not what I was expecting.
Well, then you take the square root of that.
Yeah. I was just off in my inverse in my
Oh,
mind. I was like, that's going to be 36, but I was totally off. It's 16. What's the square root of 16? 4. Right, we know that the n value needs to be a whole number, so that 0.97, just rounding errors. N initial is 4 for part C.
So then it goes from 4 to 2.
Yep. If you have a drop from 4 to 2, you get a wavelength of that. I guessed 5. That's not bad,
Yeah,
right?
not bad.
But that's because I'll tell you why. I guessed 5.
Well,
I
yeah.
know n equals 3 produces n3 to n2
Mhm.
produces like green light. I didn't count my lines correctly. N4 to N2 should produce like a purple light. Because I just know the hydrogen emission spectrum. I've taught this class a couple times. Like
Yeah.
we spend a lot of time looking at hydrogen emissions. I know what the lines should be. That's how I could guess 4.
Mhm.
Remember, and that's something important to keep in mind, that familiarity, that intuition, that's really what makes it so we can do everything we're doing.
Because it all follows a pattern.
Yeah. Right? So just being familiar with it lets me kind of like jump ahead of it. Did we have, so with that you could do the rest and you were doing the right thing?
Yeah, I had it all correct, but I forgot it was n initial squared, so all of mine were the n I squared, all my answers, so
right.
I just went back and changed them.
You just got to
Other
square
than
root
that,
all of them?
yeah.
Cool. Great.
That is an important thing because the squared.
Yeah.
I think that it goes from N16.
Yeah,
and
so
you're like,
I-
wait a second, that'd be way.
Yeah.
It's a big drop.
It'd be a big drop. Be a lot of
Yeah.
energy.
Did we want to look at any of their homework questions, or should we look at some lab stuff?
Honestly, laptop would be good too.
Okay.
We didn't do any quantum numbers, correct? We haven't done that yet.
No, we have not. That's why, unfortunately.
And we did the probability distribution at all?
Not yet. I mentioned it a couple times, but we
Yeah.
haven't formally gone over it,
Okay. So
which is why the homework stopped. So,
Because 1 through
it's-
7, 14, 15?
yeah, 1 through 7, 14, 15, and the rest of homework 1.
Okay. Yeah. And that's all like atomic numbers.
Atomic numbers and isotope masses.
Yeah.
Mm-hmm. So why don't we observe the wave motion in the real world? Just because we said number 7 really quick. It should be a pretty simple one.
It's on the order of 10 to the minus 19 joules.
Okay. Super, super small.
Yeah, it's just not observable to us. You know, quantum phenomena, these like the quantum properties we talk about, which we incorrectly say are like wave particle properties, like it's both. It's really just quantum properties, but we don't understand it besides saying it's kind of a wave and it's kind of a particle, but it's not really either. It's like some like overlap of the
Duality thing.
two. Yeah, the duality thing. It's really, we should be saying quantum properties, which we observe as either wave properties or as particle properties, but it's just quantum properties.
Mhm. And it was an n final of 1, your ultraviolet,
Yes.
and then n final of 3, your infrared.
Yep. So n
For
final
the
equals
hydrogen.
1 for hydrogen,
hydrogen.
right? So you'll notice on your equation, I'm pretty sure your equation sheet also has the modified Rydberg equation. It has like a z squared in there.
Yeah.
Oh yeah.
That is for when you want to do non-hydrogen atoms.
Ooh.
Because Z is your number of protons. So
True.
remember, all of this Rydberg equation and all of this came from solving the Schrödinger equation, which depended on the Coulombic attraction, that positive-negative charge attraction to the nucleus. If you increase the number of protons, you get stronger attraction. It modifies your energy.
Yeah. Okay.
Would that, when you add in the z squared, is that still the Rydberg equation, or now is it something
I call it the
different?
modified Rydberg equation.
So there's a question on the lab write-up. It says, can the Rydberg equation be used for all atoms? Would you just say if you factor in
I would
the,
say if you factor in
The
the
number of protons.
the number of
number-
protons?
yeah, if you factor in, well, I would say if you factor in the effective nuclear charge, but
The effective-
number of protons is good,
Okay.
right? We're going to talk about effective nuclear charge later.
Okay.
I got a quick question on number 4. So, it's just labeling each transition as according to emission and corresponding to absorption. I get
Uh-huh.
that part, but then putting the list in approximate order of increasing energy transition, smallest to largest.
Yeah. So this is asking us, remember how I just mentioned, like, we're trying to develop intuition?
Yeah.
This is, instead of doing calculations, it's just kind of like, go with your intuition, like,
I may have just figured it out because I remember the diagram going down from 1 to 2 is a large transition. And then
Perfect.
2 to 3.
yeah, yeah.
Okay,
Having
I'm
that
good.
intuition in the back of your head is exactly what that
Okay,
problem's
got
trying
it.
to get you
Actually,
to
yeah,
do.
that helps me a lot. So.
Yeah. So, and we know, do you know the reason why the 1 to 2 is bigger than the 2 to 3? Just bigger than 3 to 4?
With the equation.
Because of the equation.
Always because of the equation.
Yeah.
That's always a great answer.
Math.
Because the math says so.
Yeah.
Remember, it's a 1 over n squared
Oh yes.
energy. So when n equals 1, this is like negative Rydberg constant. When n equals 2, this is like negative Rydberg constant over 4. When n equals 3, this is negative Rydberg constant over 9. When n equals 4, this is negative Rydberg constant over 16.
Yeah. Okay.
The difference between 1 and a quarter is much larger than the difference between a 16th and a 9th.
Yeah.
And as you go up and you keep going to the next one's 25th, the difference between a 16th and a 25th
Is even smaller than 9 and 16.
is the inverse n squared.
Got it.
What did you say again for the all atoms, as long as there's the nuclear charge to take it into account, or
For the problem that asks if you can use the Rydberg
for
equation.
all atoms it was
So that question is essentially if you take into account the change in the Coulomb force.
okay.
Is the simplest way to put it, which the equation you have on your equation sheet says it adds a z squared to say, the more positive charges you have in your nucleus, the stronger the Coulomb force is. There's an extra modification we can do where we say, okay, but if you have extra electrons, those are going to push the electrons away more than that's going to counterbalance the attraction to the nucleus because you're going to have this push away. So that is where you get this idea of the effective nuclear charge. So you got your nucleus, you got a bunch of electrons kind of in a cloud around it, right? And then you got one more electron out here, right? If you've got 15 protons in that nucleus, that electron is not going to be attracted to all 15 protons because it's also going to be repelled by 15 electrons or 14 electrons. So in order to talk about this attraction through the electron cloud, we use this term, the effective nuclear charge. We're going to talk about that more later.
Okay.
That's just if you wanted to go that extra level of understanding of how would we modify the Rydberg equation to deal with any atom. Because, it works for hydrogen because hydrogen is simple. There's one proton, one electron. if we want to do this for something that's more complicated, we need to take into account all of the electrons, all of the protons, all of the repulsion terms. Let's look at this real quick. This is, let's say you got a nucleus, and you got 3 electrons. Electrons attracted to the nucleus. So that would be each electron moves, right? So each electron moves in space. So that's going to give us, each electron is going to have a kinetic energy term. That's going to be 3 terms in the Hamiltonian. We'll call it kinetic energy 1 plus kinetic energy 2 plus kinetic energy 3. Then each electron is going to be attracted to the nucleus. We'll call that plus potential energy A1 plus potential energy A2, A is for attraction, plus potential energy A3. But
It's also going to be repelled.
each electron is also going to be repelled by each other. So then you're also going to have plus, oops, I changed colors. I didn't mean to do that. You're going to also have plus potential energy repel 1, plus potential energy repel 2, plus potential energy repel 3. It just starts getting really complicated. That's just with 1 nucleus and 3 electrons. Imagine if you add a 4th electron, you're adding another kinetic energy term, another attraction term, and you're going to be adding 1, 2, 3 more repulsion terms for adding 1 more electron. And it just goes kind of exponential growth from there. So it becomes very nice to just say, hey, we're going to approximate it into the C effective. And say that anything that's like closer to the nucleus essentially counts as like a spherical shell of charge. Oh, I don't know how much physics you've all taken. That's okay. Right. Well, I mean high school physics too. Other homework questions, we've done 3, 4, and 14. If you have questions on those, we'll come back to them. But I want to get the rest of their questions answered, and we can come back to those. Lab questions? Let's do some lab questions.
Okay. In number 3, it says draw an energy diagram of the first 6 energy levels. Is that just what you
That's
had
what
on
I
the
just
board?
erased.
That's what you had on the board?
Yeah, so this
That
is
equals 1.
Just to clarify.
so post lab. Number 3 is, yeah, you're just going to do something like this.
Okay.
And then you can put your transitions in there, right? I think it asks you to do that as well.
Yeah. For the
I didn't do
ones
the
that
right
are-
ones, but yeah, this is essentially the picture it's asking for. Should of course put an axis on there of energy. I always forget to put my axis on there because everyone knows what this picture means, but you should always, I mean not everyone, but everyone knows.
Everyone knows.
Everyone. But just for the few that don't, we should put axes on there. And we can label these n equals 1, n equals 2, so on and so forth. But everyone knows. So that's number 3. Other questions from lab?
Number 7 says one of the wavelengths of light emitted by an excited calcium ion is 393 nanometers. Calculate the energy and calculate the energy emitted by 1 mole of atoms. So,
Oh, interesting.
do you have to take into account that there's 20 electrons?
No. So I instantly thought that. I was like, oh, wow, I didn't realize there was a question in the post lab that had you use the modified Rydberg equation.
Okay.
And then I realized you don't need to. Why not?
Because it gives us the wavelength.
It's just asking for the energy, right? Since we have the wavelength, we can say that the energy of the photon is equal to the change in energy of the atom, absolute value, right? We can just go with that.
and then you'll get that in joules, and you'll do
Will you multiply it
multiply it
by
mole.
the
Yeah.
number of atoms?
Okay.
Yeah. So remember, this is going to give us joules per photon. And then we're going to multiply by 6.02 times 10 to the 23rd photons per mole.
But wouldn't it be atoms per mole?
Or-
Why?
Well, yeah, photons are atoms. Right? So remember, this is just a counting number, so it can be anything we want here per mole, so we can do atoms.
Oh.
But how many photons does each atom
That's
produce?
what's throwing me off. Okay.
Well, also, how many photons does each atom produce? One. So the number of
Okay.
atoms is equivalent to the number of photons. Of course, that's an oversimplification because an atom can like emit a photon and then be relaxed and then emit another photon. Like
I think
all
that's
kinds of
what
weird
was
things can
confusing
happen.
me. Okay.
Right, we can always like introduce extra complications. For example, in those arc lamps, it's not like every atom emits one photon and then it's like, oh, all done.
Yeah.
Like we can re-excite the atoms using electrical energy and they can continuously emit photons. But there needs to be some excitation.
Mhm.
But
Okay.
other lab questions?
Number 8, it talks about first ionization energy.
Oh.
So it says calculate the ionization energy for hydrogen atoms. Does that just mean use the delta E equation with n final equals infinity?
Yep.
And n initial equals
Did it
1?
define ionization energy for
It
you?
does.
Cool. Yep, that's it.
I just skipped that.
That is approximately correct. Well, I guess for a hydrogen atom it's pretty accurate. For the other atoms, it's going to be approximately correct because you have to use the modified Rydberg equation. But yeah, that actually works pretty well.
Okay.
So the outermost would be the n initial being infinity, or
And final.
and final being infinity.
Right, so this is removing an electron, so you're going to go from the ground state, and you're going to excite it so it's completely at the highest energy possible, like it's completely knocked away.
Okay, so n final equals infinity.
Right, so ionization energy is removing the electron, putting energy into the atom.
Okay.
And number 9 talks about energy levels in sodium, and it gives you the energy difference in joules, and asks calculate the wavelength. Would you just use the E equals HC over lambda? Okay.
Delta E equals, yep, same thing. You notice, even though there's a lot of problems,
There's a lot of the
Pretty
same stuff.
Yeah.
pretty common theme, right? And each of them has just like a slight tweak to it. So if you're not understanding the underlying concepts, it feels like totally different problems.
But there aren't that many equations to work off of, so there's only so many questions you can ask with so many different equations.
But then that's the really wonderful thing I think about having a lot of problems on it is like you get to see how applicable it is to all of these different situations when it's all really the same thing. I mean, I could write you a question about the absorption lines or the spectral lines in nuclear magnetic resonance, and that's in the radio wave spectrum. But it's still just a 2-level system. You calculate the difference in energy, and you get like what frequency is that associated with.
Mm-hmm.
That's it. It's the same thing. All spectroscopy, all things where we're using light to look at atoms and molecules is 2 energy levels. What's the difference? What's the wavelength? All of the the sprays I did into the fire and we saw light come out. Like if we measured the wavelength of light, we could have figured out what energy transitions we were actually driving. It's all actually the same stuff. So that was number 8. Number 9 was just a quick conceptual question.
10 is like number 3 on the homework. It gives us 1,000 watt microwave oven.
Yep.
And then 11 and 12 with the diagram spectrums.
And is it the Hofbauer lines? I think I'm remembering the name wrong.
Fluorescent lamps and solar emission spectrums.
The from
totally got it backwards, the Frohoff lines, yeah.
Yeah.
Whoops. That has to do with the, so if you look those up, I don't want to spoil it.
Yeah.
It's a quick look up.
Okay.
And you read it and you're like, oh, interesting.
And then you can tell based on the spectrum which one of these things emits a line spectrum and which one emits a continuous spectrum.
Uh-huh.
Okay. And that's all it's asking.
Yeah, it's just conceptual.
I think I'm
Cool.
good then. That's
Good,
all my
good.
questions.
Okay, I'm gonna go ahead and stop the office hours because I don't know, is anyone even watching? No. There's one person watching, but I think it counts me watching myself right now, so nobody's watching.
Nice.
Oh, heartbreaking.